Hi, my name's Albert, and I'm a grade 12 student at Lizard Collegiate Institute in Ottawa, Ontario, and I'm super excited to be presenting my project today at the SBC Innovation Summit. So my project focused on Alzheimer's disease, and that's because I think Alzheimer's disease is the most formidable challenge that we face as a species because of how complex the brain is and how complex the disease is itself. Now, unfortunately, right now, when we study Alzheimer's disease, we study the overall changes that happen in Alzheimer's disease over the entire brain. What's happening overall, bulk, so to speak. But the problem is that the brain isn't static. The brain isn't the same everywhere. Different changes happen in different cell types at different times in Alzheimer's disease and other diseases in the brain. And so I wanted to look at Alzheimer's disease at a single cell level, at the finest resolution possible. And so I analyzed single cell data that was publicly available. And so the first step was to cluster these cells. And when I did that, I got 6 clusters. And then I subclustered each one of these clusters to figure out the major components of the cluster, or subtypes, so to speak. And so I found out that certain subtypes were specific to control cells, but other ones were specific to Alzheimer's cells. And so the hypothesis there was that these Alzheimer's associated subtypes could drive the disease in Alzheimer's. And there were also subclusters in each cell type that had both Alzheimer's and control cells, and that speaks to the functional conservation of cell types in between Alzheimer's and control as well. Now, I wanted to find out then, where do these Alzheimer's specific cell subtypes come from? What other subtypes do they originate from? Because they have to come from somewhere. And so I conducted pseudotime analysis, and what I found out was that each Alzheimer's associated subcluster originated from a specific control associated subcluster. And from there, I designed an algorithm called TranscriptoRank. Now, TranscriptoRank takes in differential gene expression analysis results and a gene regulatory network, and it finds out transcription factors that are able to reverse or promote the conversion from one cell subtype or one cell type to another. And so I applied this in 2 different ways. So I applied TranscriptoRank to converting Alzheimer's specific subtypes back to their original state from healthy cells. And I also applied it to the subclusters which had both Alzheimer's and control cells to figure out what transcription factors could turn those Alzheimer's cells in that subcluster to the control version. And so what I found out was that there were certain transcription factors that were conserved throughout both of these processes. So for example, heat-inducible factor 3 alpha. TranscriptoRank said that downregulation of that would result in conversion between Alzheimer's disease states to control states, whereas upregulation of NPAS3 would promote the conversion from Alzheimer's specific cells to control cells. Now, both of these transcription factors are extremely poorly characterized and haven't been well analyzed, especially in the context of Alzheimer's disease. And so this represents promising therapeutic avenues. And so overall, TranscriptoRank identified more than 60 of these transcriptional regulators, some of them which are well characterized, which proved its robustness as an algorithm, and some that are less characterized. And all of these transcription factors all have strong potential for therapeutic avenues in Alzheimer's disease. Now, I also analyzed cell-cell signaling pathways that change between Alzheimer's disease and control, as well as metabolomic flux changes. So both of these are also crucial for driving Alzheimer's disease or preventing its emergence. And so what I found when I analyzed cell-cell signaling pathways were there were some pathways that were conserved. So for example, the MHC pathway in microglia was upregulated, same as the CXCL pathway in microglia and astrocytes. But for example, the osteopontin pathway, the SPP1 pathway, was upregulated, and that's not well characterized in Alzheimer's. And so the SPP1 pathway contributes to mitochondrial dysfunction and inflammation. And so it's a potential driver of mitochondrial bioenergetic disruptions in Alzheimer's disease, whereas pathways such as NRG3 or NRX1 all serve as synaptic plasticity mediators to promote neuronal survival and synaptogenesis and axonogenesis. And lastly, I analyzed the metabolomic flux changes that happen in Alzheimer's versus control. And I found that certain metabolic modules, such as hyaluronic acid synthesis and metabolism, amino acid synthesis and metabolism, were downregulated in Alzheimer's, whereas pathways such as glycosaminoglycan synthesis, urea cycle, and glycolysis were upregulated in Alzheimer's. And these are all potent therapeutics at the metabolomic level for targeting Alzheimer's disease. Now, ultimately, I identified transcriptomic, signaling, and metabolomic targets in Alzheimer's disease that I hope will serve as the next generation of therapeutics against Alzheimer's disease and help contribute to the curing of this devastating disease once and for all. Thank you so much for listening.